Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about design of shear reinforcement for singly reinforced beams, which is a continuation of our previous class. The outcomes of today's lecture are like this. On completion of this class, you will be able to know what are the design steps are there for design of a shear reinforcement for singly reinforced rectangular beams. After knowing these steps, you should able to design by your own for given parameters. You have to design singly reinforcement for the shear reinforcement for the singly reinforced rectangular beam. So let us recall the things what we discussed in our previous class, that is last class. We have discussed about shear stress distribution in RCC beams, types of shear reinforcement are provided, and what are the shear effect. So let me give a brief discussion on these three topics. Say we have generally we have two types of beams. One is heterogeneous beams and homogeneous beams. Homogeneous beams means you know that it is made up of a single material, that is a concrete. If you see the stress distribution for that homogeneous rectangular beam, it is a parabolic in nature. In the topmost fiber of the beam, that shear stress will be 0, and at bottommost fiber of the beam, the shear stress also 0. At a neutral axis, the shear stress will be maximum. That maximum shear stress can be calculated by using that 3 by 2 of tau average. So this is all about your homogeneous beam. Next, coming to the heterogeneous beam. Heterogeneous means the beam which is made up of two different materials. Here in this beam we are using concrete along with steel. So as here we are using two material means we can call it as a heterogeneous beam. The best example for this heterogeneous beam is RCC beams. So if we have discussed what is the shear stress distribution in these heterogeneous type of beams, here we have observed that at the topmost fiber of a beam, the shear stress is 0. At neutral axis, the shear stress is maximum, and from neutral axis, the centroid of the steel reinforcement, the shear stress is constant. But for calculating shear stress in the RCC beams become a complex phenomena. To overcome that problem, our code IS 456-2000 has given one simplified equation, that is in terms of average shear stress or the nominal shear stress, that can be calculated by tau v, that is tau v is equal to fact v by shear force by area into that area of that particular cross section. And this is how we seen regarding the shear stress distribution in RCC beams. Next, and as we know that we have to design the shear reinforcement. If you design the shear reinforcement, what type of shear reinforcement you have provided, what are the forms you have to provide. Generally, we will provide in three different forms. One is in terms of vertical stirrups, second one is a vertical stirrup with a bent up bars, and third one is a inclined stirrup. I have seen all those figures in our previous classes. So generally vertical stirrups are provided provided around the tension reinforcement, and at the compression zone this stirrup will be hanged, or this stirrup will be tied with a hanger bars. Generally these stirrups are provided with a diameter of 6 mm to the 16 mm, and based on the intensity of shear force we can use what type of vertical stirrup reinforcement is used, say single legged, double legged, or multi legged, so on. We have those are chosen based on their intensity of shear force. Then we have a shear effect. What is the shear effect? Why should we provide this shear reinforcement? Those things we have discussed in shear effect. For this we have chosen one particular beam, that is a simply supported beam subjected to a UDL throughout. In that section, in this beam tension zone of that particular beam, we have chosen three elements, and one is at support, another is at midspan of the beam, and another is in between somewhere on the support, between the support and midspan of the beam. And we have analyzed those three elements. From that we have concluded that at the midspan that we will get a vertical cracks, that is there only we have only bending, there is no shear force, because in a simply supported beam subjected to a vertical loading, we have the maximum, there is the center of the beam, we have the maximum bending moment and shear force is 0. And we come on to the supports. A support we have a bending moment is 0 and shear force will be maximum. For that case we will get a cracks, that is a diagonal crack because of that only shear force, there will be a tensile force will develop at that particular element of the beam. The tensile force will induce tensile stresses. Those tensile stresses are try to pull that element so that they can split across that in the fashion of diagonal of the beam, so that there will be a diagonal cracks will occur. So to counteract the diagonal crack, we have to provide a shear reinforcement there, and that the crack which is appear at the support will be, that is because of only shear, so the cracks will make an angle of 45 degrees with the horizontal of the horizontal axis of the beam. And one more element we have chosen, that is at the mid somewhere between the support and the midspan. Here the cracks will appear because of shear as well as a bending. At that particular point, we will get shear force and bending moment. So the cracks will appear because of shear and your bending moment. So that's why those cracks are in between, the angle of those cracks are in between 45 degrees to 90 degrees. So those are the things we have discussed in detail about this shear stress distribution, shear reinforcement, types of shear reinforcement, and shear effect in the beam. Right. Now in this class we are going to discuss what are the design steps are available for design of shear reinforcement in the singly reinforced rectangular beams. The first step would be determine the ultimate shear force using support condition and type of loading. Here, if in the problem if he give the support type of beam and type of loading and type of support condition, based on that you have to calculate ultimate shear force. Say if in the problem if we give if you want to design a shear reinforcement for cantilever beam with uniformly distributed loading, we know that the maximum shear force occur at a fixed support of a cantilever beam. At that particular place, the shear force, maximum shear force or factored shear force or ultimate shear force will be Vu equal to W into L. So this is a factored shear force and this is factored load. This normal load which is acting on the beam, that should be multiplied with a suitable factor of safety, that is 1.5. In the case with a simply supported beam, if it is subjected to a UDL over the beam, then the maximum shear force occur at the support, that value of the maximum shear force will be Vu is equal to WUL by 2. That is, again it is a factored load. So it is a with respect to the problem given, that is it is useful in your examination. If you want to design actually practically a beam where you exactly want to take the shear force, for this code has given one provision that we have to take the shear force, we have to calculate the shear force at the critical section of a beam. What do you mean by critical section? The section where factor or ultimate shear force is calculated, that section is called a critical section. So generally, as per IS 456-2000, this critical section will be taken a distance d, small d from the support. Small d from the support. What is small d here? Small d is effective depth of the beam. That means finally I can say the critical section will be taken. It is at a distance of effective depth, that is the depth distance equal to the effective depth of the beam. At that particular section we have to take a critical section, and there we have to calculate what is the ultimate shear force. That is when we are designing practically a particular beam, that criteria have to take in. But anyhow, when we are writing a board exam or diploma, board exam or university exams, he will mention you we have to calculate the ultimate shear force at supports only. Anyhow, we will get the ultimate shear force at the supports only for a simply supported beam as well as a cantilever beam. So by like this we can calculate what is the ultimate shear force is. Then the second step would be we have to calculate nominal shear stress. You know, the nominal shear stress can be calculated by using IS 456-2000 according to the clause number 40.1. That is, tau V is a nominal shear stress is equal to Vu by Bd. Here Vu is a factored shear force and Bd is nothing but width of the beam, B is width of the beam, and D is effective depth of the beam. If we substitute those values in this formula, we will get what is the nominal shear stress, or I can say average shear stress is. Then third step is we have to calculate the maximum shear stress, that is tau C max. Why should we calculate the maximum shear stress and how it will be calculated? It is the only reason for calculating this is we have to compare our nominal shear stress and obtain maximum shear stress. Based on this step, either we have to design the shear reinforcement or whether we have to redesign the section again. That we can obtain from this step. Here the maximum shear stress can be calculated according to table number 20 of IS 456-2000. As already discussed that the maximum shear stress of a concrete is dependent upon the grade of concrete. That is, if for a particular grade of concrete like M15, M20, M25, M30, M35 up to M40 and above, we have their respective tau C max value. Suppose if in the problem it is given that M20 grade concrete, what is the tau C max for that? The M20 grade concrete, the tau C max value will be 2.8 Newton for mm square, and you get some value for nominal shear stress. If that nominal shear stress value greater than the maximum shear stress of a concrete, then no question about that, we have to go for redesign of the section. That means we have to reduce the shear force again, and then we can make our maximum tau C value should be less than the tau C max, right? If the nominal shear stress value is less than the tau C max obtained by using this condition, then we go for the further step, right? Like that, this maximum shear stress value useful for design of shear reinforcement. Next, step number 4 is calculation of percentage of steel, and it will give what already we have designed that dimension of beams and amount of steel reinforcement required for that particular beam according to the limit state of collapse in flexure condition. So the reinforcement required is AST, and these are the width of the beam and effective depth of the beam. By using this formula, that is percentage of steel is equal to 100 AST by BD, we will get what is the percentage of steel will be provided in that particular singly reinforced rectangle beam. Right, by obtained values of by obtained percentage of steel and according to the grade of concrete, we can calculate what is the design strength of the concrete, that is a tau C. So it is a very crucial step here. This can be calculated. See, this tau C value can be find out from the table number 19 of IS 456-2000. That is, on here in the vertical direction they have given a percentage of steel, or I can say it is a row, and here they have given in this horizontally they have given a grade of concrete. Suppose if you want to know a design shear strength of a concrete for a particular percentage of steel and a particular grade of concrete. So for example, I will take here, so 1% of tensile reinforcement and M20 grade of concrete, what will be the design shear strength of a concrete? Say this is a 1% and this is a M20 grade concrete. So if you see in horizontally like this and vertically like this, we will obtain this value. This value will be the design shear strength of a concrete, that is equal to 0.62 Newton for mm square. Like this, we will calculate the design shear strength of a concrete. During the process of design, we may come across the value of percentage of steel in between the values which are not available in this table. Then what we'll do? We may know the minimum value and the maximum value. Between this minimum and maximum value, your required value may fall. For that, we have to go for interpolation technique. From the interpolation, we can calculate what is the desired design strength of a concrete. So, for example, here, if we want to know a design percentage of tensile steel is say 0.7%, and a grade of concrete given is M20. For that condition, you want to calculate what is the design shear strength. Say, but if I observe the table, I have only direct values for 0.5% of tensile reinforcement corresponding M20 value, that is 0.48, and I know after 0.5%, I have for 0.75% of tensile reinforcement, I have what is that design shear strength of that particular concrete, that is 0.56. But I want to calculate, what is the design shear strength for 0.7 percentage of tensile reinforcement? So that means your value may obtain between 0.48 to the 0.56. This value can be calculated by using a linear interpolation technique. So this is all about your design shear strength. Next step would be a minimum shear reinforcement. How much minimum shear reinforcement will be provided, and which condition we have to provide a minimum shear reinforcement. Those things we'll discuss in this step. If your design shear strength is greater than the nominal shear stress of a concrete or average shear stress of a concrete, then only we have to design or we have to adapt the minimum shear reinforcement. If if condition fails, then we go for separate design of shear reinforcement. So say for this condition, let us assume that our design shear strength is greater than a nominal shear stress of a concrete as per class number 40.3 of IS 456-2000, and give in this class a subclass is there 26.5.1.6 of IS 456-2000. The minimum shear reinforcement for a stirrup shall be provided according to this formula. So in this formula we have, that is ASV. ASV is nothing but total cross-sectional area of a stirrup legs effective in shear. And you know the width of the beam. SV is the spacing of stirrups along the length of the member, and that is Fy is yield strength of a steel that should not be greater than, that is 415 Newton per mm square. According to this, we can calculate what is that ASV is. That is, see, ASV by BSV greater than or equal to 0.4 by 0.87 F5. It may be greater, equal, or it may be greater than this value. So for it is provided when your design shear strength is more than nominal shear stress of a RCC member. Right. This is important and crucial step in design of shear reinforcement. That is a design of shear reinforcement. When we go for design of shear reinforcement, we go for design of shear reinforcement when your design shear strength of a RCC member is less than nominal shear stress of a RCC member. In last slide we had discussed, that is opposite to this, that is our nominal design shear strength of a RC member is greater than nominal shear stress of a RC member. Then we have provided nominally, anyhow we have to provide shear reinforcement, but this case we have to separately design. Right, our designing may be in according to this design, we can place a shear reinforcement in three different forms, as we have already discussed. One is only vertical, or another is only inclined, another type is vertical stirrup with a bent up bars. Say according to the class number of 40.4.4 of IS 456-2000, the design of shear reinforcement of a bent single bar or a single group of parallel bars are bent up at the same cross section. That means a bent up bar provided in I can say prismatic bar. What do you mean by prismatic bar? Prismatic bar means a bar having a cross sectional area same or constant throughout its length of the bar or length of the beam. So this formula will be useful for prismatic beams. Say if you are using a bent up bar, then VUS, here VUS is strength of the shear reinforcement, that can be calculated by using the formula 0.87 Fy ASV into sin alpha. You know already that Fy is yield strength of a steel, ASV is the area of stirrups which are provided in the beam section, and alpha is the angle between inclination of stirrup or a bent up bar and with the axis of the beam. Generally that will be provided as a 45 degrees. So this is how we calculate a shear strength of, or a strength of shear reinforcement in bent up bars as well as in inclined stirrups. right? See here, this is very important step again. As per class number 40.4, the shear to be restricted by stirrups and bent up bar is VUS equal to VU minus tau C into BD. So what do you mean by this formula? If we go to the actual concept, that nominal shear stress or average shear stress in RC member is equal to sum of shear force, shear stress in concrete and shear stress in steel. Sum of those two, call it as a shear stress or nominal shear stress, that is VU, or simply I can say the stress induced, the force induced become by that shear stress will be shear force. That this shear force is it is a factored shear force. It is a combination of shear force in concrete plus shear force in steel, right? That equal to total shear force acting in the member. So exactly what if you want to calculate what is the shear force to be resisted by that steel alone, that is VUS, that equal to VU minus tau C into BD. How this value is obtained? We know that VC, say VC is the shear force restricted by concrete. That VC can be calculated as we know that stress is nothing but force by area, and from that force can be calculated multiplication between, that is stress and area. Here, because of that shear force in the concrete, the shear stress is occurred is a tau C. This tau C multiplied by area of cross section of a steel, that will give me the what shear force in the concrete. So we know that is factored shear force in RC element is equal to a factored shear force in steel plus factored shear force in concrete. From that I want to calculate what is the shear force to be resist in steel, that is VUS equal to VU minus VC. That VC value should be substituted, that is tau C into BD. So this is how we calculate what is the VUS in, that is strength of shear reinforcement. So this is a total strength of shear reinforcement. Here shear reinforcement may be placed in a three different fashion. That may be a completely vertical or a completely inclined or combination of vertical and bent up bars. In case you are providing in a beam a shear reinforcement in the form of a bent up bars as well as vertical stirrups. In this situation, the shear force will be taken by bent up bars of 50% and remaining 50% will be taken by the vertical stirrup. Now we have to design already we have a bent up bars. Those main bars will be bent at the near the support at an angle of 45 degrees. Where anyhow those bent 50% of shear resistance taken by that bent up bars. Next we have to resist the shear force remaining 50%. For that we have to design a vertical stirrup. So if you get to among the 100%, we have to design our shear reinforcement with respect to vertical stirrup by considering 54% of shear resisting capacity of a beam. Though sometimes when we are calculating, you may get the shear resisting capacity of bent up bar may be more than 50%. That should be restricted to 50% or less than that. But remaining 50% or remaining balanced percentage of shear resistance, for that we have to calculate what is the number of vertical stirrups are required, what is the diameter of vertical stirrup to be provided, and what is the spacing should be provided. According to the remaining 50%, we have to design vertical vertical stirrups. Right. Suppose you are using a vertical stirrup alone, then that VUS equal to 0.87 Fy ASV D by SV. Here it is the SV is the spacing that we can calculate by according to your minimum shear reinforcement condition, that is Fy you know, ASV have already calculated, and D know effective depth of that. From that you can calculate what is the shear resistance of a vertical stirrup. And for inclined stirrups, this is the criteria that VUS can be calculated 0.87 Fy ASV into D by SV into sin alpha plus cos alpha. You know that ASV is a minimum area of reinforcement provided as a vertical as a shear reinforcement. Fy is the yield strength, and D is the effective depth of the member, S is the spacing provided, and alpha is the inclination of a bend, inclined stirrup with respect to the horizontal. Generally that will be considered as a 45 degrees. Then the last step will be the spacing of stirrups. How much spacing we have to give? The spacing can be calculated based on the following condition. That is, spacing, first condition is spacing obtained from the minimum shear reinforcement when we have designed the minimum shear reinforcement. When our tau c is greater than tau v, then we go for a design of minimum shear reinforcement. Then that is the first condition, and second condition will be 0.75 into effective depth, and third condition is 300 mm. We will provide minimum of these three values as spacing of stirrups. So this is all about your design steps. Based on this design step, now we will solve some problems, numerical problems on design of shear reinforcement. Say the first problem in this condition, in this design of shear reinforcement is the ultimate shear force at a section of a RCC beam is 200 kilonewtons. See, clearly given it is a ultimate shear force. That means it has given directly VU. But sometimes he will give a type of beam and condition of loading over the beam, and say if we give simply supported beam subjected to UDL over that, definitely will get the maximum shear force at the support. That is a simple shear force or simple design shear force. That design shear force should be multiplied with a suitable partial factor of safety, that is 1.5. Then we get what is the ultimate shear force. But in the case of this problem, he has directly given what is the ultimate shear force is. If he gives a beam condition and type of loading, then you can approach that method, that is by calculating, if you are using simply supported beam, that is WL square by 2, and the W should be multiplied with 1.5, then we will get WU into L square by 2. Like that we have to calculate what is the ultimate shear force. But in this problem, VU is 200 kilonewtons, and next the width of and effective depth of the beams are 250 mm and 500 mm. See, he has mentioned width as 250 mm and effective depth as 500 mm. Sometimes in the problem he will not mention any depth, simply will give depth is 500 mm. For that you have to consider as a overall depth. From that overall depth you need to calculate what is the effective depth by assuming suitable effective cover. But in this case of problem, he has given only what effective depth. So effective depth is small d equal to 500 mm. And he also mentioned that what is the percentage of tension reinforcement. The percentage of tension reinforcement provided is 1%. And by giving this data, what is the intention to calculate here? We have to check the adequacy of section to resist the shear and check whether shear reinforcement is necessary or not for using M20 grade of a concrete. That means with this data, it is adequate to provide shear reinforcement, or if it is adequate or it is necessary to design the shear reinforcement or not, that we have to calculate in this problem. So with respect to this given data, the given data is VU equal to 200 kilonewton, B is 250 mm, effective depth is 500 mm, and percentage of tension reinforcement is 1%. According to that, first we have to calculate what is tau B is. Tau B involves nominal shear stress, that is factored shear force by area of cross section. As already given that is factored shear force is 200 kilonewtons, but that is we have to convert that into the newtons. That is 200 into 10 power 3, and he has given B and D. B is 250 and D is 500 mm. If you calculate this, we will get 1.60 Newton for mm square. The next step we have to calculate is maximum shear stress. Right? From table number 20 of IS 456-2000, the maximum shear stress can be calculated based on the grade of concrete given. The grade of concrete given is M20. The corresponding tau C max is 2.80 Newton for mm square. Right, see, if you observe that in this condition, our nominal shear stress is less than tau C max. So that we can say if the section is adequate for shear consideration. If this value is opposite to that, tau v is greater than tau c max. We have already discussed. If it is greater than, then we go for redesign of section. That's why we are checking before design of section whether it is adequate or not, that we have the adequacy or not, that we are checking. So to have the adequacy for providing shear reinforcement, the nominal shear stress should be less than that maximum shear stress tau c max. So we have, by using that, there we have your nominal shear stress is 1.6 and the maximum shear stress is 2.80. That is the tau c max is greater than tau c your nominal shear stress. So we can say it have adequacy for providing shear reinforcement. Right. Next we have to check is whether we have to provide shear reinforcement or not. That can be calculated by establishing the relation between nominal shear stress and design shear strength. So design shear strength can be calculated by using table number 19 of IS 456-2000. So given percentage of steel is 1%, given grade of steel concrete is M20. So this is 1% of steel and grade of concrete is M20. 1% and M20 will get design shear strength is 0.62 Newton for mm square. So from this I can say our nominal shear stress is greater than design shear strength of the concrete. So that we have to definitely go for design of shear reinforcement. So according to this problem, so shear reinforcement is necessary. So this is how we calculate whether it is adequate or it is necessary or not for providing shear reinforcement, that we discuss based on these steps. So next problem will be determine the spacing of two-legged 8 mm dia stirrups for RCC beam of 230 mm wide and 450 mm effective depth to resist the ultimate shear force of 85 kilonewtons and grade of concrete is M20 and grade of steel is 250 used. Right, here the question is somewhat different. For what spacing, if you provide for particular spacing, if what spacing will resist this shear reinforcement in the beam when you are using a M20 grade and Fe250 steel and the dimension of beams are 230 mm by 450 mm effective depth. So according to this problem, we have to write the given data. The vertical stirrups are having the shear resisting capacity must be VUS equal to 85 kilonewtons, width of the beam is B equal to 230 mm, effective depth of the beam is D equal to 450 mm. See, the spacing can be considered with respect to two different criteria, say A, B, C, like that. According to criteria A, spacing should be calculated by using the formula. So SV is equal to 0.87 Fy by ASV D by Vs. Then how to calculate this ASV? In the problem, it was mentioned that what is a two-legged 8 mm dia bars. How many legs are there? We have a two leg for, so 2 into pi by 4 into d square will be area we can calculate by using this formula, that 2 into pi by 4 into d square. As it is 2 is mentioned because of it is a two-legged. If it is a four-legged, we will place 4 here. So 2 into pi nothing but 3.14 by 4 whole multiplied by the diameter of bar given is 8. So if you simplify this or if you calculate, we'll get the value of ASV is equal to 100.50 mm square. So already effective depth you know, Fy you know, and you know what is VUS is, that is a strength of shear reinforcement. By this formula we can, if you substitute all those values in this formula, we'll calculate what the spacing is. So after substituting that is 0.87, Fy is 415, ASV is 100.50 and D is 450 by VUS is 85 kilonewton has given. I'm converting that in terms of Newton, so that is 8500. So from that the spacing will be obtained is, that is 115.70 mm. According to the criteria 1, we get criteria A 115.70 mm. The next criteria will be B, spacing from minimum shear reinforcement consideration. So if you want to design, if you have to provide a shear reinforcement minimum, then we have a formula that ASV by B into SV is equal to 0.4 by 0.87 Fy. From that equation we can calculate what is the spacing will be. The spacing will be calculated by crisscross this 0.4 into B by 0.87 into ASV into FY. If you substitute the value of B, ASV and Fy, you will get what is the spacing is. So 0.4 multiplied by width of the beam given is 230 and ASV have calculated is 100.5 mm square and grade of steel used is Fe 250, that is yield strength of the steel will be Fe, that is 415. From that the spacing obtained is SV equal to 237.6 mm. And another condition allowed is, in that we have two separate conditions. One is 0.75 times D or another is 300 mm. Among these we have to provide lesser value. So if you calculate with respect to the first condition 0.35 into 450, you will get 337.5 mm and R 3 mm. Right. If you check, if you compare the conditions like A, B, C, will get for a value will be less, that is 115 mm. So we have to provide spacing for the stirrup minimum of criteria A, B and C. According to the comparison, we get the minimum value of spacing of stirrup is 115. Hence, provide a two-legged 8 mm dia stirrups at a spacing of 115 center to center. So this is the detailing of that. So this is a beam. These are the main reinforcement. This is a support, and this vertical line will showing you what is the shear reinforcement, that is in the form of stirrups. The spacing means it is the spacing between two bars. This two bar will be provided in this particular problem, that is 115 mm center to center. So this is about this particular problem. Next we have another problem, that is an RCC beam 230 mm wide and 450 mm deep is reinforced with 4 bars of 16 mm dia of a grade of steel is 215 provided in tension zone, and if the design shear force is 60 kilonewtons, design shear force is 60 kilonewtons, the shear reinforcement consisting of only vertical stirrup by using grade of concrete is M20. So the whole meaning of this problem is, for given B and D and provided area of steel and given grade of concrete and grade of steel, we have to calculate the shear reinforcement, the spacing and amount of shear reinforcement. The form of shear reinforcement we are provided with respect to this problem is only vertical. But this vertical stirrup should have to resist the design shear force of 60 kilonewtons. So according to this problem, so I can say the ultimate shear force or a design shear force VU is equal to 60 kilonewtons. Width of the beam is 230 mm and overall depth as given there. It does not mention that is the effective depth or a overall depth, that we have to assume that as a overall depth. So overall depth is 450 mm. From that overall depth you have to calculate what is the effective depth. Why? Because we need to use effective depth any formula here. The assume effective cover of 50 mm and calculate what is the effective depth is. Effective depth is equal to 450, that is overall depth, minus effective cover assumed is 50 mm. From that 400 mm will be your effective depth. And we have to calculate area of tension reinforcement. The area of tension reinforcement given in the problem is, that is 4 bar of 16 mm dia. So AST equal to 4 multiplied by pi by 4 into 16 square. From that we will get what is the AST is, that is 804.3 mm square. So now follow our basic design steps. That is, first we have to calculate nominal shear stress, that is tau V, that can be calculated by using this formula VU by BD. Here VU is a factored shear force, that is in the problem it is given that in kilonewtons, but we have to convert into the newtons, that is 60 into 10 cube by 230 into 400. 230 is the width, 400 is the effective depth. So the nominal shear stress obtained from this formula is 0.65 Newton per mm square. The second step would be calculation of maximum shear stress. This can be calculated by using IS code table number 20 of IS 456 2000, and for given grade of concrete, what is the maximum shear stress is. So the given grade of concrete in the problem is M20 grade. The maximum shear stress corresponding to M20 grade concrete is 2.80 Newton for mm square. Right. So if you check the adequacy that between tau V and tau C max, here tau V is less than tau C max, so it is adequate to provide shear reinforcement. Right. Next will be to calculate the percentage of steel. You know, calculating the percentage of steel, we have a formula that is AST into 100 by BD. AST we have already calculated, that is 804.3, and multiplied by 100 by area of cross section, that is 230 into 400. From this we'll get the percentage of steel is 0.874 percentage. Then by using the percentage of steel and the grade of concrete, we have to calculate what is the design strength is. The ultimate aim of calculating design strength is, as we really want to provide shear reinforcement or not. So that means that can be known from the relation between nominal shear stress and design shear strength. Here see, for calculating design shear strength, the percentage of steel is like this and grade of concrete is like this. We have obtained that percentage of steel is 0.874 percentage, but for that we don't have a direct value. That value falls between 0.75 and 1.0. Corresponding to the 0.75 value for M20 grade concrete, we have a 0.56 is a design shear strength, and corresponding to 1 we have a 0.62 Newton for mm square as design shear strength. So if we have our value is between these two, so we'll be get definitely our design shear strength value will be between 0.56 and 0.62 Newton for mm square. By using interpolation technique, we'll get what is the design shear strength is. After interpolation, we'll get the design shear strength of a concrete for M20 grade concrete per particular percentage of steel, that is 0.874 is 0.59 Newton for mm square. If you observe this value is in between 0.56 and 0.62. Now compare your values. Generally tau C we got is how much? Tau C is equal to 0.65, and now we have got a tau C max is 0.59. If you compare this, your tau V is greater than tau C, hence we can say we have to go for design of shear reinforcement. Right. Next step will be minimum shear reinforcement. So when we go for minimum shear reinforcement, when it satisfies this condition, that is your design shear strength is greater than nominal shear stress, then only we go for providing minimum shear reinforcement. But according to this problem, we have get a condition that our tau nominal shear stress tau V is greater than tau C, so definitely we have to go for design of shear reinforcement. Now how to design the shear reinforcement? Right, here we have separate steps for designing shear reinforcement, as we had discussed already in our design steps. First we have to calculate what is the design resisting capacity of a concrete, then we have to calculate what is the design resisting capacity of a shear reinforcement. So design resisting capacity of concrete will be VC, that can be calculated by tau C into BD, as I already discussed how we got this formula. So this is a force and this is a stress, it is a area. The stress nothing but force by area. If you want to know the force nothing but by stress multiplied by area. So this is a shear stress corresponding to concrete, and this BD is the area of cross section of a given member, and VC is the shear force resisted by concrete. So we know that tau C is 0.59 multiplied by 230 into 400 or the dimension of a beam. So this amount of force will resisted by concrete, that is 54.28 kilonewtons. Then calculate what is the shear to be resisted by shear reinforcement, that is total shear reinforcement, the total stress we know, the total force we know. From that if you deduct the shear resisting capacity of concrete, that is VC, then we can know what is that shear resisting capacity of a reinforcement, that is VU is equal to VU minus tau C BD. We know VU is total minus VC means shear resisting capacity of a concrete, that equal to tau C BD. So we know the total is 60 minus what is the shear resisting capacity of concrete, that is 54.28. If you calculate that, you will get the shear resisting capacity of a steel, that is 5.72 kilonewtons. So for particular shear force, this particular shear force, we have to design our shear reinforcement. Right. For this, let us provide a 8 mm dia of two-legged vertical stirrups. For that, we have to calculate ASV. As we are providing two-legged, the area of ASV is that is 100.5 mm square, and spacing of the particular this according to our basic formula. Spacing of shear resistant VUS equal to the spacing SV equal to 0.87 FY ASV D by VUS. We know what is FY is ASV from this formula, and D is effective depth. VUS is already known, that is 5.72, and if you substitute all those values, we will get 0.87 into 415 into area of stirrup, that is 100.5 into 400 effective depth by that is shear resisting capacity of a steel, that is 5.72 actually kilonewtons, that we have to convert into the newtons. So 5720 will get the spacing obtained from this condition is 2537.4 mm. This is a criteria A. Like that, we have to calculate spacing with respect to criteria B, that is with respect to the minimum shear reinforcement provided. Then from minimum shear reinforcement, SV can be calculated by ASV into 0.87 FY by 0.4 into B. If we substitute all those values, we will get what is SV is. From this, we will get 394.4 mm. And the final criteria is maximum allowed spacing. That is, we have two criteria here, sub criteria. That is 0.75D, another is 300 mm, which in this we have to take minimum value. So if we calculate with respect to 0.75 into D, so D is 400. With respect to this criteria, we will get 300 mm. Another criteria is 300 mm. Among these, 300 will be the less. So if the spacing of vertical stirrups should be provided lesser value of criteria A, B, and C. If we check all these criteria, we will get the criteria C will give us the minimum spacing. So we have to provide the spacing corresponding to the criteria 3, that is 300 mm. So finally, hence we have to provide two-legged 8 mm diameter stirrups at a rate of 300 mm center to center. So these are the detailing of that. So it's a beam. These horizontal bars are the main reinforcements. These are a vertical stirrups. They have to provide a spacing of 300 mm center to center. So this is 8 represents the 8 mm dia, 2L nothing but two-legged stirrups at what is the spacing 300 mm center to center. So let me summarize today what we discussed. We have started the design steps. We have following design steps. First we have to calculate what is the nominal shear stress. Then we have to calculate maximum shear stress. Then we have to compare whether this tau V and tau C will give the adequacy to calculate the shear reinforcement or not. That adequacy can be calculated by checking the relation between tau V and tau C. If tau V is greater than tau C max, tau V is greater than tau C max, then only we have the adequacy for providing shear reinforcement. Then we have to check tau V and tau C. Tau V is the nominal shear stress. Tau C is the design shear strength. If your design shear strength is less than that tau V, then we can go for design of shear reinforcement. For design of shear reinforcement, we have to calculate what is the total. We know what is the total shear force has to be resisted by the total member. In that member, we have a concrete and a steel. In that, we have the share of concrete and share of steel for resisting the shear force. We have to calculate what is the share of concrete to be resist, what is the share of shear steel to be resist the shear force. Those we have to calculate. Then according to that, we have to design the shear reinforcement. After that, we have to calculate spacing as per given guidance by IS 456 2000. So this is all about today's lecture. Thank you.